When we are talking about recursion, the word repetition comes to mind. The Russian nesting doll is a good example of recursion. When you open up this doll, you will find a smaller doll inside it. This pattern will keep repeating until you find the smallest doll. The similar pattern can also be seen in Romanesco broccoli. The flowers of this broccoli are made out of same patterns that resurfaces again and again when you zoom in. This is known as fractals. Trees, coastlines, mountains, and many other things in the universe possess the recursion property. Computer science is no exception. In computer science, recursion can be defined as a process in which a program calls itself. It is useful when we are trying to solve problems that can be broken down into smaller similar problems. Let's take a look at one example. In order to know your number in a queue, you need to add 1 to the number of the person in front of you. You will first have to ask the person their number. If they also do not know their number, they will need to ask the person in front of them. Notice how the equation has been adjusted. The situation repeats until we find the person at the number 1 position. Now, we can finally find our position number in the queue. To write recursive function, you need parameters, stopping condition, stopping value, recursive function, and revised parameters. And this is our general form. This is the code for the previous example. And this is our recursive function of the code. We have length as parameters, length equals to 1 as our stopping condition, return 1 as our stopping value, and 1 plus turn with the parameters of length minus 1 is our recursive function. And the output is number 4. Recursive codes can also be written in iterative form. This code does exactly the same as the code before, with the only difference this time is that we are using the loop structure. Now, let's take a look at the difference between recursion and iteration. Recursion codes are shorter, hence more elegant code. This is because it uses the control structure. The downside is that it is more complex to code, and it takes a greater time and space complexity, therefore it has worse performance. Iteration, on the other hand, are much longer because it uses the conventional loop structure. Because of this, it makes the coding much more easier and has better performance. Iteration is widely used in demanding tasks such as video games and simulations, while recursion is often used in simple tasks such as file directories.
Assalamualaikum, I'm Akmal and I'm going to show you time and space complexity analysis of recursion. Time complexity measures how time taken by program grows with the input, and space complex is measure how space or memory consumed by a program grows by the input. So without wasting time, now let's jump to our example. Let's take a look at this example factorial program that calculates factorial of n. Now let's assume that time taken to calculate factorial of n is equal to Tn. To analyze time complexity of a program, we make assumption that each simple operation costs us 1 unit of time. Comparing n with 0 is one simple operation, thus it costs 1 unit of time. Next, multiplication operation on n with function called factorial n minus 1 also costs 1 unit of time. And lastly, we perform subtraction to calculate n minus 1, which is costs us 1 unit of time. So from here we can conclude that Tn is equal to Tn minus 1 plus 3 unit of cost for simple operation only if n larger than 0. While for n equal to 0, Tn is equal to 1 because we only do comparison of n and 0. Now we can reduce Tn to our known value, which is T0. Tn minus 1 can be written as Tn minus 2 plus 6 and can be further reduced to Tn minus 3 plus 9. From here we can say that if we want to reduce by generic k, we will get Tn minus k plus 3k. Now we want to express in terms of T0, so in this case n minus k will be equal to 0 or k equal to n. Thus the equation will be reduced to T0 plus 3n, and since T0 is 1, we just substitute Tn with 1. From here you can say that time taken for this particular program for input n is directly proportional to n. This is also known as big O of n in terms of time complexity. Now, let's analyze space complexity of recursion, and for this time, we will using same example as before. At the right side is a computer memory with some partition or unit in memory which is divided. Let's say we want to calculate factorial of 5. Now, in function factorial 5, the program called another function which is factorial 4 recursively. Now, being that the function factorial 5 still not be done yet, and all local variable and current state of execution in the memory, and we'll go ahead with factorial 4 first. Now again, factorial 4 makes call to factorial 3 and factorial 4 saved in memory, and factorial 3 makes call to factorial 2 and the process occurs until factorial 0. All these states of function are getting stacked in the memory. From here we can see, even though we did not declaring any variables explicitly, but the memory is consumed by states of this function. We also can say that implicit stack is growing in the memory when recursion is executing. From this recursion tree, maximum depth is equal to 5. So if it is a factorial of n, maximum depth of this recursion tree is equal to n. So for these particular cases, space required by the program is directly proportional to input n. As soon as we reach factorial 0, function continue by return to function factorial 1, and after it done, it get removed or pop from stack and program continues until factorial 5 is finished and return to its caller. So from here, we can analyze that recursion in terms of time complexity takes more time to execute even it is simple code. And in terms of space complexity, it requires more space and memory even it is simple code. So you might ask, when to choose recursion? Only choose recursion when we need to keep code short, simple and elegant, and also time and space to be utilized by a program is not a main concern during creating the program. So I hope this helped you in analyze. Thank you.
Next, here are some scenarios that use the concept of recursion. The first one is reversing an array. We can solve this problem with either using iterative method or recursive method. But this video will focus more on recursive to make the concept easier to understand. Consider we have an array with 5 elements inside them, which is 2, 3, 4, 8, and 9. And we are required to reverse it into 9, 8, 4, 3, and 2. How does the concept of recursion explained earlier help us to solve this problem? Now, let's examine the snippet of the code. Here, we have a method called reverse, which accepts 3 parameters from the main method. The reverse method is divided into 3 parts. The first part is the terminating statement. This statement compares the position of index in the array. It will start with the element in the first index and the last index. Then it will slowly reduce until the value of start index is greater than or equal to the value of an index. When the terminating statement is satisfied, it will return the array values to the main method and the reverse array will be printed. The second part of the code is the reversing process. If the terminating block is not satisfied, the values inside start index will be stored in temp and will be overwritten in the end index. It will proceed until the condition statement is true. The last part is the recursive call statement. When the reversing process is done, it will proceed to do recursion by adding 1 to start index and minus 1 to the end index. The process will continue until the value of start index is greater than or equal to the end index. This is a simple demo on how the code works. We input the value for the array size. Then we enter the desired values inside the array. The output will be printed reversed as expected.
Assalamualaikum warahmatullahi wabarakatuh. My name is Haneef bin Salim and I will be explaining the details of the Sierpinski Gasket's application of recursion. So first, I will be explaining the definition of the Sierpinski gasket. Sierpinski gasket, also known as the Sierpinski triangle, is a fractal attractive fixed set with the overall shape of an equilateral triangle subdivided recursively into smaller equilateral triangles. It is one of the applications of recursion where its recursive function includes multiple recursive calls. Now let's see a step-by-step visual of the Sierpinski gasket and see how it works. First, you take a regular equilateral triangle and you divide the triangle into 3 different triangles inside the first triangle. That will result in something like this. Then for each triangle inside the first triangle, you divide them into 3 more triangles, and this will lead to something like this. So this repeats infinitely unless it reaches the maximum level of recursion, which is set by the user. So now we will get into the algorithm of the Sierpinski gasket. For the recursion function, this is the main function where the recursion occurs. It will be a void function, and it includes the parameters x, y, l, level, and max. X and y refers to the xy coordinates of the bottom left corner of the initial triangle. L refers to the length of the current triangle, and level refers to the level of occursion of the current triangle, and the max refers to the max level of the triangle. So for example, this is what a function would look like for the recursion function. So to find the new points of the 3 new triangles, the divide function has to be called 3 times inside of it. This is where the recursion occurs, multiple recursion. So the first call is for the triangle that appears at the bottom left of the current triangle. This is what it will look like. The second call is for the triangle that appears at the bottom right of the current triangle. This is what it will look like. And the third call is for the triangle that appears at the top middle of the current triangle. And this is what it would look like. Using sine pi over 3 to find the angle of where the top corner is, top vertex. So once the level of recursion reaches the max level, the triangle is drawn. This is an example for the code. So here is an example of a 3-level Sierpinski gasket where when the level is 1, it will divide into 3 because level 1 is just an equilateral triangle. When it reaches level 2, it will divide it into 3 more triangles, and once it reaches level 3, that's when it starts to draw the actual triangles. And this is what the 3-level Sierpinski gasket will look like.
Hi, my name is Farhan and I'm going to explain on how recursion can be used to build a 10 by 10 maze. The algorithm that we are going to use is called recursive backtracking. Let's first talk about the fundamentals on how to build this maze. From a programmer's perspective on solving this maze, we would like to label each of the grid with the bit value on which walls to be broken down. The bit values are represented here. If it's 0001, then the north wall is broken down. If it's 1000, then the west wall will be broken down. Now that that's out of the way, we will see how recursion is useful to solve this maze. There will be scenarios in this maze where all the neighbor cells have been visited and the maze reaches to a dead end. Luckily, with the use of recursion, the maze backtracks its steps and go back until it finds a grid that still have neighbor cells that are unvisited, and the process of building the maze continues. This is possible because all the function calls are all stored in the stack and can easily be popped off, allowing the maze to backtrack. This allows the maze to continue to execute from the previous function call available on the stack. Once all of the cells are visited, there will be no more neighbor cells to go to. The maze backtracks until the first starting point, which also means that the maze is finished. Now that each of the cells are assigned with the values indicating which walls to be broken down, we can easily print the maze however we want. Now we will take a look at the code implementation for this maze. We have a variable called bit here, which represents which walls to be broken down. Also, a variable called opposite bit, which is initialized to 0. Objects are created to represent the new and current cell. Next, we will use this random function to create a random direction. Here is how the maze moves, which is the x coordinate of the current cell is added to the x direction. Same applies for the y coordinate. Here we check if the cell is still inbound. If the cell is inbound and the cell has not been visited, then the following process occurs. The current cell will receive the bit value of the direction. The new cell will receive the bit value for the opposite direction. This is because when, for example, the cell here breaks down its right wall, the cell here needs to break down its left wall. Then, the function calls itself and the values of the new cells are given. This is called recursion.